Versa, last time there was one question from your side, I remember. Huh. Okay, so let me open that slide. Okay. Okay, yes. If I remember correctly, the question was that what we will do if there is a variable which is supposed to take only negative values, right? Okay. So I could not, find out in books, particularly mentioning that if a variable, what will be the transformation, method when your variable can take only negative value. But one thing we can do one more transformation, and we can introduce one more variable. Say we are introducing one or more variable, say zi. Okay, and we can define that zi is equal to minus xi, right? So in that case, your this new variable zi will become positive. What's that? Yeah. So that way we can by introducing this new variable zi equal to minus xi, and then you can say that your zi will always take positive value, right? Yeah, and you can use this transformation then for the new variable your zi. Okay, I think this will solve our purpose. I have not solved any problem, but I think this will work because now we have introduced new variable. So using this intermediate transformation, we can solve the constraint which are having only negative values. Okay. Yes, yes. We will solve that problem for Jedi by considering it is a positive value. But ultimate value of your xi will be negative, na? Because xi will be, yeah, minus Jedi, right? So you will get positive value for Jedi, but your final value of your variable required, that is xi, will be negative, right? Yeah, yeah. Okay. From my side, I will stop discussion in module 5. Okay, because there are some important topics in module 6, and that is the integer programming. And when I was going through it, there is a prerequisite. Some of you have might done this course OR in your previous semester. Okay, so those who have gone, for them, I will be taking some revision topics. But for those who have not gone through this prerequisite, this will be a new added topic, although it is not mentioned in your syllabus. Okay, but we need to cover those particular topics before starting your module 6. Okay, so in particular, let me tell you which portion we will require. uh, okay, just a second. Okay, so in module 6, we have integer programming, then we have non-traditional optimization algorithm, binary and real coded genetic algorithm. Okay, so these are the major topics in your module 6. And in particular, your integer programming, it is expected that you must have studied your linear programming problems in OR. Okay, so how many of you have opted OR in your previous semester? Anybody who has opted? Rajiv, Subham, Tripti, Varsha. Anybody you took? कोई नहीं लिया पिछले सेमेस्टर? Okay, so in OR there is one topic, linear programming problem. Okay, so linear programming problem, you can say you can, in terms of optimization problem, you can say that these are the problem which are having equality constraint. Okay, equality constraint, or sometimes inequality constraint may also be solved, but some tricks are some modifications are required. These inequality constraint problem are converted into equality constraint problem by introducing some variable. Okay, so that part, before going into deep into integer programming, I will, in the next class I will take one or two examples of linear programming, and how we can solve linear programming problems with equality constraint and inequality constraint. Okay, so for solving these linear programming method, there is one method which is called simplex method. Okay, so in the next class, not today, I will take up this part, and today just I will introduce this topic, that is a integer programming problem. Okay, so talking about integer programming problem, what are the integer programming? Okay, so in order to understand integer programming, let us understand what we have understood in optimization techniques till now. Okay, so in optimization techniques till now, which we have discussed, your variables, your design variables can take any value. Okay, so why these can take any value? Because these are assumed to be continuous, and they may have fractional values also. Okay, suppose for example, the thickness of plate may be 2.6 mm, 2.5, or your working hour, labor hour may be 3.34, 3.35 hours. Okay, it may be 3 hours also, it may be 3.5. Okay, also weight of some material may be 1 kg, 2 kg, or it may also be in fraction 1.75, 1.78, something like that. Okay, but in some engineering situation, you may find that your design variables have some discrete values. They may have certain values like 0, 1, 0.5, 1.0, 1.5, something like that. Or they may be, like one example, that the diameter of your heat exchanger may be an increment of 1 by 8 inch. Okay, so this will be, say, for one cell this is 1 by 8, then for another cell it may be 1 by 8 plus 1 by 8, that is 1 by 4 inches. Okay, so something like that you may find. So these kind of values are called discrete values. Okay, then there may be problems where fractional values are not allowed. Okay, so, or they are not practically feasible, or they okay, so like saying a 1.5 number of manpower. Okay, so there cannot be a value that 1.5 man. Okay, either it will be 1, or either it will be 2, 3, 4, 5. So this will be a integer value. Okay, similarly there are in boiler requirement in thermal power station, so it cannot be 1.6, it will be either 1 or either 2. Okay, 1.9 workers in a project, 2.67 lathes in a machine shop. So while solving optimization problem mathematically, you may get fractional values, but practically these values are not possible. These are not practically feasible. Okay, so we have to choose. We have to solve our optimization problem in such a way that you get the optimum value. Also, it is a integer value, it is not a fractional value, so that you are able to get exact optimum solution of your problem. Okay, So sometimes you suppose if you have found some requirement that there are only 2.76 leads required. Okay, so in that case, sometimes you may round off your fractional part. You can say that there will be requirement of 3 lathes. There may be a requirement of you can say two, if it is 2.16 you can say 2 lathes. Okay, so sometimes it works, sometimes it does not work, because these variables are again dependent on several other variables. They also affect each other, and might be possible that rounding off is not going to work. Okay, so how this rounding off, what is the issue with the rounding off? Okay, and how we take up, we get solution of such kind of problem, we will discuss today. Okay, so in integer programming, I hope you are able to understand why what is the term integer programming. In integer programming, your optimization problem can take only integer values. Okay, so that is why these problems are called integer programming problems. Okay, so there are four conditions, four, one, two, three, four conditions. First condition is that when all your constraint can take only integer value in an optimization problem, then it is called an all integer programming problem. Okay, similarly, when the variables are restricted to take only discrete values, the problem is called discrete programming problem. So discrete means the values may be like I told in previous slide, that there may be like diameter of heat exchanger may be an increment of 1 by 8 inches, or it may be 3, 6, 9, something like that. Okay, so there may be a continuous increment or decrement in the design variable. Okay, so these kind of optimization problem are called discrete optimization problem. Okay, then in some cases there will be mixed type of problem, where only few variables, that is some it is written some variable, or you can say few variables are restricted to take only integer values, and rest can take discrete values. Okay, so these kind of problems are called mixed integer or mixed discrete programming problem. Okay, then there may be a fourth kind of problem where your design variable are allowed to take on values either 0 or 1. Okay, so either the value may be 0 or a value may be 1. So these kind of problems are called 0-1 programming problem. Okay, this is a short introduction about integer programming problem, and now we will these are the different methods. We will come on this slide at a later stage. Okay, so now we will try to understand integer programming problem graphically. Suppose this is a case of a linear programming, and in which we are having a objective function maximize fx equal to 3x1 plus we are having a objective function fx equal to 3x1 plus 4x2, and which is subjected to the constraint 3x1 minus x2 is less than equal to 12, 3x1 plus 11x2 is less than equal to 66, x1 is greater than 0, x2 is greater than 0. So because this is a case of maximization, what we will do, we will first draw your I think in the starting of your this course optimization problem, we have discussed graphical method. Okay, so in graphical method what we do, we decide feasible region. Okay, so for this particular problem, that is optimization of this particular problem, what we will do, we will try to find out the feasible region based on your constraint. Okay, so suppose x1 is greater than x1 is greater than 0. So for x1 is greater than 0, this will be your line, and any value which is in the right side of your y-axis. Okay, so this will be your feasible values, all values lying in the right side of your y-axis. Then similarly for x2, so for x2 all the values above this x1 axis. Okay, so these all values will be your feasible values for this particular constraint, that is x2. Then we have another constraint. Okay, from this we could find out that the feasible values will be in the first quadrant. Okay, then we need to see the remaining constraint, that is 3x1 minus x2 is less than equal to 12. Okay, so let us see where is this line. This is here. 3x1 minus x2 is equal to 12 or less than, this will be particular region in that side. Okay, in this side this will be your particular feasible region. Okay, so if you see this is your third constraint, 3x1 minus x2 equal to 12. This is the line corresponding to this constraint. Then we have another constraint, that is 3x1 plus 11x2 is less than equal to 66. Okay, so this is the line corresponding to this particular constraint. Okay, so if you see you are getting a feasible region A, B, C, D, A. Feasible region is A, B, C, D, A. Okay, I hope the feasible region is visible to all of you. A, B, C, D, E, A, B, C, D, A. So in this feasible region, what we will do, we will try to find out the point which can have highest value for which of highest value of your objective function. Okay, so for graphical method, as I told that we give certain value to your objective function, and we try to shift your objective function. We try to find out the solution by shifting your objective function curve. Okay, so here if you see we have this value f corresponding to f equal to say equal to 31. Okay, so we are starting from a value that is 31. So we have drawn this particular line f equal to 31, or you can choose any value. Suppose you have value f equal to 36. You are starting from 36. Let us not start from 31. Okay. So this is the line corresponding to f equal to 36, and when you are moving towards your feasible solution, because this line is out of your feasible region. Okay, when you are trying to move towards feasible solution, which point is going to touch first? Okay, so this point C will come in contact of your objective function as compared to other point. Okay, so this will come in contact first, and you can say that point C is having the optimum solution, or which correspond to the maximization of this particular program. Okay, so C, what are the values at C? Values are x equal to uh, 5.5, and y equal to, or you can say x1 equal to 5.5, x2 equal to 4.5. Okay, so th- this way you could find out your solution of your objective function, that is the maximization of fx equal to 3x1 plus 4x2. But since it is a integer linear programming problem, what is the restriction? You cannot have fractional values. Okay, since you cannot have fractional values, what you will do, you will round off your fractional part, and you can say that because these values cannot be greater than this 5.5, it should be less than 5.5, and x2 should be less than 4.5, otherwise the solution will go beyond your feasible region. So which values, if you want to round off, which values will lie in your feasible region? These will be 5 and 4. Okay. I hope you are able to understand why we have not rounded off it as 6 and 5, because these values will go beyond your feasible region. Okay, so the values, the integer values which are lying in your feasible region, these are 5 and 4. So for this particular problem we can say that if it is a case of integer programming problem, that the optimum solution will be x1 equal to 5 and x2 equal to 4. Okay, now we will try to see whether this kind of rounding off works every time or not. Okay, so because for this particular problem, having this much constant, it is working. Okay, but there may be the case that this rounding off is not did not work, and you may come up with a situation that your that solution through your normal optimization problem is quite different while we are taking solution of integer linear programming problem. Okay, so we will try to see one example. Okay, let us try to re-examine the same problem, but we have changed the constraint. This constraint we have changed. Instead of previously we have one constraint line, that is 3x1 plus 11x2 is less than equal to 6. Now we have changed this constraint, which is equal to 7x1 plus 11x2 is less than equal to 88. Okay, so all these constraints are same, x1, x2 and 3x1 minus x2. So we can easily find out the feasible region. So for feasible region, the feasible region is A, B, C, D and A. Okay, so this is your feasible region. And what is our objective function? Objective function is the same, that is 3x1 plus 4x2. Okay, so in the similar way we will find that through graphical method, the values which correspond to the maximization of this particular objective function are 5.5 and 4.5. Okay, then we have this constraint that is 7, these subjected to this constraint. Okay, suppose we round off, then your solution will be 5 comma 4. Okay, but when you try to see that when you are shifting your this objective function line, that is f34.5, then f32 and f31. Okay, which is corresponding to 31, 32 and 34.5, and you will see that after this value, that is f corresponding to 34.5, you are finding that there is one value, that is f32, which is corresponding to your objective function 5 comma 4, constant values 5 comma 4. Then but then again your there is one value f equal to 31. Okay, so here we can see when we are in the previous problem we were able to get the next round of value which was equal to 5 comma 4, but in this case the next round of value is your 8 comma 0 comma 8, sorry. Here the next rounding of value which is lying on this objective function or the next integer possible values are 0 comma 8. Okay, you put these values 0 comma 8, so this will be f equal to 32. So here we can see instead of f equal to 31, your next possible integer set of values is 0 comma 8, because this particular corner of your or the point is satisfying the integer values as well as maximization of your objective function. Right, in the earlier case, which was the solution, f equal to 32. Okay, sorry, f equal to 31. Here the solution was what was the optimum value, 31. But here because 32 is also satisfying the integer the constant which can optimize or which can maximize your integer programming problem. So these values are 0 comma 8, and here you can see there is a quite difference between the point is you know there is a huge difference between these points, that is 5.5 and 4.5. They have no correlation between these two points. Okay, so here in integer programming problem we may come up with such kind of issues where your rounding off may not work. Okay, so this is all about a short introduction on integer linear programming problem. Okay, and in the next class, as I have told, that we will take up linear programming problem, one or two example. In single class, I will try to explore one or two example using your simplex method. Okay.